Okay, welcome everybody. So it's not such a big group anymore, I guess. Okay, as far as I know, all the conflicts, these scheduled conflicts, they were resolved. What is my, well, my video has disappeared for some reason. Okay, for instance, Zoom sessions on Wednesday, they moved to Thursdays. Okay, so I hope everybody is aware of this, that in the next period we will have Zoom sessions on Thursday instead of Wednesdays. So this is the change because there was this conflict. Another thing is that exams are also the conflicts between exams were also resolved. So the some exam was moved somewhere. Our exam remained on Wednesday. Okay, this, as it was planned originally, but there was this conflict. But I think the other exam had got moved to some other spot. Okay, so. Also, next time is going to be a practical session. Tessa and Lena, they're going to set up a Zoom meeting. So they didn't do this yet. I already changed things on the Canvas page. So in next period, there will be Zoom sessions on Thursday. So I've changed the Zoom meeting data. So everything is there, of course. So it's not going to be this meeting anymore. So the data will be changed because it was a recurrent meeting on Wednesdays, but it's not going to be on Wednesdays anymore. So I had to change the data of the Zoom meeting. Otherwise, things are the same. We will stick to our schedule as planned originally. Okay, now second assignment is going on. So hopefully, so I got some questions here and there. One thing in the last exercise of the second assignment. So this is the real data, and it might be that you try your initial values and your NLS procedure fails. That's normal. Actually, I had to look for these initial values for a long time, and I found ones which worked. But the thing is that when you run them, when you run this procedure, then you have this. You need to fill in a 1,000 array, and then there's just one failure is enough for Bootstrap procedure stop and report an error. So you might get like, I don't know, maybe 600 filled in, but then 600 first is going to sort of fail for some reason because it's a Bootstrap. Each time it's sort of it's a different data set. So you actually need to run it many times before you get the result. So for instance, for my initial values, I have to run like 3, 4, maybe 5, sometimes 6 times before one time is actually when I get the whole array filled. Okay, then there is no error. Okay, so that's so let's just try to find the right initial value. This is the main. If you don't succeed, okay, let's try to do this for several days at least. Then I will give you mine. Okay, I will give you mine initial value, and then well, that works at least for sure. For if you try this several times, then there will be one time then it works. Okay, so this is. But actually, it would be much better if you find initial values yourself, even argue how you found them. If your reasoning is sort of the right one, and also your initial values are the ones for which your procedure works, that would be just great. That would be, it would be sort of, you will get full points for that. Okay, so let us go back to, okay, Can the t-distribution quantile that are necessary for exercise 1 of the assignment be computed in R? Yes, you can. Yes, well, why not? I mean, of course, t-quantiles. I mean, what else can you do? Otherwise, you will have to go to look up in the book in the tables, of course. Do we have to get them from a table or something? No, just from R, of course. Just compute them as usual in R, but otherwise the rest is of course done by this is theoretical, and just only t-quantiles you could compute by R. In principle, of course, when you do all these computations, you can of course check those by performing them also in R. Okay, so you're supposed to do everything theoretically, but in principle, of course, in this particular case, you can check, right? You can sort of have control. Whatever you computed, you of course can compute also in R as well. Okay, and then you could compare what you did theoretically, what R does. Okay, let me start with the lecture. So here it is. Oh, it's this, the very end. Okay, let's just repeat what we did so far very shortly. So we had, now we have a nonlinear regression model, remember? So we had F linear, but now it's nonlinear. Okay, that's the difference. We make a step towards generality. We're going to generalize we generalized already our linear model just by allowing this function to be not necessarily linear. It's now nonlinear. Otherwise, it's the same setting. Okay, in principle, it's the same setting as before when we had linear model. So the only difference is this function is allowed to be nonlinear with respect to theta. Okay, with respect to x, it was already allowed to be nonlinear. Okay, it was not a problem. So what we assume here is that this is basically the imposing the model. Okay, so when we assume something on epsilons, this is restricting all possible settings to just particular one. And particular one, so the epsilons there, they must be independent. We don't assume them to be normal, by the way, but they have to have, of course, expectation 0 and variance sigma squared. That we need. Okay, we also need that they're independent, but they might be, by the way, distributed differently. Okay, not necessarily identically distributed, by the way. But of course, it would be nice if they're normal. Okay, and then at the end of the day, we can also check whether they're normal or not by looking at the residuals of our fit. Okay, we will fit the model and we'll look at the residuals, and we will have errors of epsilons, and then of course we can always check whether they're normal or not by looking, for instance, at QQ norm. But in principle, it's not required for this model. Okay, again, and then we do the same as we did for linear regression. We just minimize the least squares, find this theta hat, okay, which minimizes this criterion. And then it's not a simple task anymore. So you could see that yourself, right, when you do this assignment. Sometimes there's all kinds of problems. There are no problems whatsoever for linear regression, of course, because this solution is just analytic. You just simply can write it down. You don't have to run any procedures. You just substitute in the formula. But here you do need to run a procedure, numerical one, and it could happen that it just doesn't converge. That's it. Just this problem may not have solution at all. So you really need to assume a good situation when the solution exists. At least, okay, maybe not. You may not find a global minimum, for instance, but local minimum might do as good as well, not bad. So it could be as good as a global one. Okay, and then we can estimate sigma squared, of course. By analogy, we divide by n minus p, but in principle, we could also we could have divided by n, but we just keep that analogy with linear regression and divide by n minus p, which is it's not a big deal actually. Okay, and then under certain regularity conditions, the mathematical theorem, there exists a mathematical theorem which says that theta hat minus theta is approximately normal. Okay, here you should remember that theta hat minus theta is a vector. Okay, so it's a vector. So that vector has approximately normal distribution with a vector of expectation 0 and the covariance matrix this. Okay, that covariance matrix. And what is in this covariance matrix? Okay, in this covariance matrix, we have a whole bunch of gradient vectors. Basically, we compute gradient vector for each observation xi. Okay, so and then we put them as a rows in this matrix V, and then that will become matrix of dimension n by p, and then of course the resulting matrix here, which is V transpose times V to the power minus 1. It has to be, by the way, invertible. Okay. And then this matrix becomes of dimension p by p. And there is sigma, of course, which plays a role. It must be there somehow, right? Because it's the parameter of the error. So it also comes in there. Of course, we cannot know this matrix. We can estimate that matrix. Estimated covariance matrix is this when we substitute everywhere instead of theta, theta hat, and we substitute instead of sigma squared, sigma hat. This is what we did. So this is the basics of this topic. And then, of course, what we can do once we have this, okay, we have this and we substitute estimated things here, then, of course, we can do testing and we can do confidence computation of confidence intervals. Okay, this is what we all did. I'm not gonna repeat this. It's all based again. This was a question in the discussion. Let me again say a little bit of explanation about this. In principle, we need to use normal quantile here because what it says here that this statistics is approximately normal. Okay, this is so. Therefore, in principle, when we test, we should use normal quantile. So using normal quantile means that we need to compare the value of the statistics, this is the absolute value of t, we need to compare to normal quantile. So we are interested in rejecting, we want to check whether H1 is true, right? That's the sort of the idea. So the hypothesis of interest is always H1. So we need to make it difficult, right? If you want to be cautious, if you want to be conservative, if we want to go for H1 only if it's really true, okay? So when is it really true? When we make this inequality more difficult to fulfill. Okay, when do we achieve this? We achieve this if we make this quantile bigger, okay? Then the deviation from the null hypothesis must be bigger. So we were being conservative in the sense that we actually believe in H0 very strongly. We think H0 is actually true. Only if data says it's really not true, it's really very extreme, only then we reject H0. And we make our testing, our rejection more difficult by using T-quantile here instead of normal quantile. So in that respect, we are not doing anything wrong here by using T-quantile instead of normal quantile. We're actually being more cautious, more conservative. That's it. That's the only. And then also, that's another reason. So that it's just analogy with the linear regression. Okay, so we are sort of making, there is approximation error here. So we are sort of trying to accommodate that approximation by being more cautious. And that's the idea. Okay, so. And the same goes for the computing these p-values and so on. So we are basically that idea of being more conservative. That sort of present here in p-value also compute interval. Okay, so we compute bigger confidence interval means we are more conservative. We say, Okay, in principle, our confidence interval is smaller because it would be based on this. For sure, to be sure that it's really a confidence interval, let's make it slightly bigger. Then we're sure it's doing the right thing. Of course, we are losing in the preciseness, right? It's not as exact as it would have been with normal quantile, but on the other hand, we are more sure. We are sort of we're sure that we accommodate that approximation error which occurs here, right? This here it's approximately. That's all. So there's nothing nothing to it. So you don't have to find very deep reasons. That's the only one basically. And we had the of theta, lambda of theta, and we actually derived the one which is called basic bootstrap interval. And there was another one, the one which would, the more natural one, which is based only quantiles, and there is no hat in our interval, and then do something with this. You get the hat, so lambda hat is in also in the interval, and of course the quantiles, the sample quantiles of our bootstrap sample. It's all there. Yeah, I don't know. People use both basically. I don't know. This one has the advantage that we actually kind of use the information we have. Otherwise, we're sort of not using it. If we would have not used lambda hat, we would not. We sort of, yeah, that would be like a waste a little bit, right? So therefore, people use this interval not to waste the knowledge of theta hat. Okay, so that would be only bootstrap, no theta hat, and here it's bootstrap and theta hat as well. Both are combined in this what one calls basic bootstrap procedure. Okay, okay, now this is something new. Now we want to, well, relatively new. Suppose we want to estimate the expected value of the just one function. We don't want theta, we want this function. Basically, we want to predict, okay, for instance, in this example, we have these concentrations, and then we, for some concentration, we want to predict a new density. Okay, the variable of interest. So that actually what we predict is just this function at some point x, and theta is unknown. So we are not that much interested in theta. Okay, this is a parameter which describes the model. That's fine. It's somewhere at the background, but we are not really interested in that parameter itself. We actually want to estimate f of x of theta. Okay, that's all. So this is just a function of theta which we want to estimate. And since we have already estimated theta itself, so we have theta, then of course we can simply substitute theta hat instead of theta, and we have something to compute. And that is usually a good predictor, okay, of the mean response. And basically that's the one which is used. That's again basically what we are doing here. If you want, you can make a very tight relation to learning theory. We are doing learning here, okay? So this is one of the examples of what people do in machine learning. When you train the model, we've trained the model, we computed theta hat, and now we want to predict, and this is what we do then, okay? We just fill in x's, whatever x's we want, and since we already trained the model, that is theta hat, then we can make a predictions, okay, from that point on. And then this x, which is here, doesn't have to be the one we observed, okay? We observed x1 and so on, xn, but it doesn't have to be. It could be anything, could be new, okay, new x coming in. And that's exactly the idea of the prediction, what one calls prediction. Okay, let's just look at the following. Well, this is now a scalar thing, right? Remember, theta hat is a vector. But f of x of theta, this is the function of theta. So it's just, it's one-dimensional quantity. So let's just take this one-dimensional quantity minus another one-dimensional quantity. This is estimated theta, and this is true theta. And then, of course, by Taylor expansion, this is the gradient times difference. Okay, here it was one-dimensional minus one-dimensional, function minus function, but here it's vector times vector, right? So this is the gradient as a vector. Think of that as a row, and think of that as a column. So here we have just a scalar product of things. So write it down as just a vector Vx transposed. Think of that as a Vx as the column. So transpose becomes row. So this is row times column, okay? What we have here, it's approximately. And this is, of course, a gradient, just a gradient computed at point x. And you just take all the derivative with respect to all the coordinates. Okay, what do we have? We know how theta hat is distributed, right? Theta hat minus theta, it has a normal distribution. And so this fact here is based on this property, okay? This property it's at the bottom of this slide. And it says the following: if we have a z, any z, which is multivariate distributed with parameters mu and sigma, this is the covariance, it's the multivariate distribution. And if we take any vector, okay, any fixed vector, deterministic vector, multiply, okay, we just take a scalar product of some deterministic vector A, multiply with z. So what we will get here is one-dimensional quantity. It's now random variable. It used to be random vector, now it's a random variable. And that random variable is again normally distributed with what parameters? Okay, well, it's simply expectation of that. It's just R transpose times mu and the variance of that. And if you compute the variance of that, you will get A transpose sigma A. So you get here, this is the number already, okay? So it used to be a matrix, but if you take a row times matrix times column, you will get a number. Okay, that's actually a quadratic form with respect to the A. Okay, this is what you will get here is some number, and that number is going to be a variance of this random variable. Okay, and that's exactly what we use here. So you see, we have something, some vector about which we know it has approximately, at least approximately, multivariate normal distribution. We multiply that vector with some other vector. Okay, we take a scalar product. Then according to this property here, it has to have this distribution. It's also normal. It's now one-dimensional. Okay, so this is just a random variable that becomes a random variable. It has normal distribution with zero mean and variance this. Okay, this is the number now. It's just a number. And then that's it. We are actually done, because now we can do testing and we can do confidence interval calculation. Again, the same problem, of course. We don't know sigma, we don't know theta. Okay, substitute all the quantities we don't know. Substitute instead of them. Substitute the estimated quantities. So we just put theta hat instead of theta. So we will get estimated gradient vector. Okay, we will, of course, substitute also those in V and then also sigma, and that's it. Now it's just exactly the same what we had before. Now we need to conclude. So just take this random variable, divide this random variable by the square root of its variance, right? Then you will get variance 1, right? Then it will become standard normal. We simply normalize this random variable. If this random variable is normal with parameter 0 and some variance, we just divide by the square root of that variance, and we will have standard normal, okay? So therefore, this has to be approximately standard normal. Of course, approximately, because we have approximately here, and also approximately because we put theta hats instead of theta, and we also put sigma hat instead of sigma. So we will make a lot of approximation errors here, but doesn't matter. We still okay approximately. So that quantity here is approximately standard normal, and that's it. So that's now we are at the stage when we do exactly what we did for the coordinates of theta. Now we can do testing, and we can do confidence interval estimation. Okay, let's do that. So for instance, we want to test whether a function is equal to some value. Usually it's 0, okay, but nothing prevents us from testing that this function is equal to some value, whatever that value is. And then against that it's not equal to that value. And then of course we simply look at this random variable. Okay, this is the statistics. We can compute that. It's supposed to be standard normal. And in principle, what we should do, we should use this normal test. But again, we do t-test, okay, t-quantile. Again, the same reason. We are being cautious. We are being more conservative. So we compare this to the value of the statistics, the absolute value of the statistics to the t-quantile. And then we reject if it's bigger than this extreme value. Okay, and that extreme value is bigger than we would use if we would use normal approximation. Okay, we could do that by we could do test by comparing to a quantile, or we just can compute p-value, or we could look whether the value a, the one we were actually testing about, whether this value lies in the confidence interval. And the confidence interval can be found as follows, okay? So this is just the estimated value of the things we are interested about, okay? Plus, minus, again, quantile, square root of the estimated variance. It's the same over and over again, okay? This machinery is just the same as we had before, many times already. And that would be just our confidence interval for the mean response for the f of x of theta. Okay, so we can basically, I would do the following. You just, if you're asked to do confidence interval and you're also asked to do the test, I would just start with the confidence interval. Okay, when you have confidence interval, then you do test also, right? So if you construct confidence interval, which is required anyway, for instance, in the exam, that's just my suggestion to you, just to make your work more efficient. You just start with the confidence interval, you compute it, and then you say, oh, okay, well, I want to test whether this value is equal to 2, say. Well, I just look whether 2 belongs to this interval or not. If it doesn't, then of course I reject H0, and that's it. So you don't need to do it separately, I would say, just by computing confidence interval, you just do both things simultaneously. Okay, what about this bootstrap confidence interval? Well, actually, we did that already, okay? Now, there's nothing really new. We did this for function lambda of theta, which was arbitrary function of parameter. Okay, what is it that we're interested about now? It's f of x of theta. Okay, x is something we should know, of course. So in principle, it's a function of theta, where x is just some fixed value which is given to us. We should know that. So you should treat this f of x of theta as some function of theta, and that's your function lambda theta, for which we did already all the computations. Okay, so nothing really new. So what we do, we just simply substitute instead of lambda of theta, which was an arbitrary function of theta, our particular function of theta, which is f of x of theta, and then apply this machinery, which we did. So this is going to be our approximate bootstrap confidence interval then, where 2f of x of theta hat minus something, okay, minus bigger, what is it? Bigger quantile, sample quantile of level 1 minus alpha divided by 2, and here minus smaller quantile, so therefore this thing bigger. So what is a quantile, sample quantile? Okay, you should remember, you just compute many like B1000, for instance, estimators, bootstrap estimators of your quantity of interest, which is f of x of theta. So you will get B estimators of those. You order them, and then you take a sample quantiles of this ordered sample of estimates. Instead of just one estimate, we used to have one estimate, fx of theta hat. We will have B of them, and we can have quantiles of this. Okay, so these are just quantiles of this order sample of estimates, bootstrap estimates. So basically, you need to run this procedure B times, and then you fill that array of estimates, of bootstrap estimates. And then it could be that one time it's just your procedure fails. Okay, and then the whole bootstrap fails basically, and then you get this. But maybe many of those will be filled in, but just one will fail, and then the whole procedure will fail. Okay, let's have a look at the example. So we have our example where we have just one x, right? So it's a C, it's a concentration C. So our function is f of C of theta. Okay, this plays a role of x. So this plays the role of y, the response. So this is optical density, whatever that means. Theta, which is three-dimensional, theta 1, theta 2, theta 3. Remember, we did already analysis for it, right? Nonlinear regression analysis. So this is a good example when you actually, things work. They could derive theta hat. You could also derive estimated covariance matrix, okay? So all of it is already done. What we want to do now, we want to predict the value of our function or your mean response at C equal to 4, okay? So what does that mean? We just need to estimate f of 4 of theta, okay? We just substitute theta hat, which we found, okay? And then we get this value, okay? So this is already an estimator of the mean response at the value of concentration C equal to 4. Okay, that would be another. Of course, we want to predict also a confidence interval, and we also want something, but at this moment we just want to compute the interval. Okay, this is our T quantile. Okay, we just take this n minus p degrees of freedom. And then this is the value, 1 minus alpha. This is 1 minus alpha divided by 2. So that means we are testing for alpha equal to 0.1, right? So because here it's 1 minus alpha divided by 2. It's two-sided. And then if we compute, okay, we need, of course, take a derivative with respect to theta 1. Okay, then the derivative with respect to theta 2, derivative with respect to theta 3. So it's going to be vector. And then we will fill in x equal to 4, and we fill in instead of theta, theta hat, the one we found. And if we do this, we will get the estimate of our gradient vector. So this gradient vector consists of 3 coordinates. So these are the 3 coordinates. And then we have to do this computation, okay? So that computation is a bit, well, it's not a lot of computation, but you do need to perform this computation. You have this matrix, covariance matrix, remember? And what you need to do, you need to take that matrix, this whole covariance matrix, which we estimated here. You need this whole covariance matrix, not just one particular diagonal element as we did for when we were estimating the coordinates. Now we need the whole matrix. So you take this whole matrix, multiply from the left by the row, right? Actually, I need to put transposed here because originally it has to be, it's a column. So by transposing, we make it a row. Okay, row times matrix times column. We will get some number. Okay, sigma will get outside of this, and then we take square root of that. That's going to be an estimated standard deviation of f of 4 theta hat. Okay, that's going to be this. Well, sigma hat will go out of the square root because it's stands secant squared. Okay, you fill in all this. You will need to perform these computations here. Okay, this whole matrix is given. Okay, but then you will have to multiply row matrix column matrix. Okay, you will get a number, and then you take a square root of that number. This is going to be this number. Okay, once you've done that, that's exactly the number you use in this margin. So quantile times, okay, first of all, the estimate f of 4 theta hat plus minus quantile, okay, that quantile times, this is what we found here, okay, this the estimate of the standard deviation, and then you do that, you could do this computation, and you get this interval. Okay, that should be easy, right? We're actually repeating the same thing over and over again, more or less, slightly with slight variations here and there, but in principle, it's the same thing. Okay, let's just have a look. Well, in this particular case, things are really very good. I would say too good. We can actually do this. You see what we did here? We did this just for 1 point. C is equal to 4, but we can do this for all of them, okay? Just take all of them in this whole interval, whatever interval is. Let's just see. It's an interval from 0 to 12, for instance. Just run this, what we did here, just do this for all C's from 0 to 12. Okay, of course, you make a grid. Okay, you cannot do it for all of them because there are infinitely many of them, but you just make a very fine grid and apply this for all these values of C, okay, it's not just 4. And then you do, and then you can make these confidence intervals for each C, and then you just draw the lower bounds of these confidence intervals and the upper bounds of these confidence intervals. And in this particular case, they look too well, okay? So this, and then you will get what one calls confidence band, okay? Confidence band means constructing confidence intervals for all values of x's, okay? In this case, C runs from 0 to 13, actually not to 12, but 13. And then you see that they're really small, okay? And then, for instance, for 4, you just go like this, and then you have to draw a vertical line, and then you will see the lower bound and the upper bound of your confidence interval, and that would be the one we have just calculated. Okay, you see that this interval is very, very small. So in this particular case, things are actually very good. Okay, let's see. This is our example. Of course, we can do also the bootstrap confidence interval. We do this for 90%, by the way. So we will need to adjust, of course, the a little bit computation of the sample quantile, right? That's the only thing you need to adjust then. You will get, of course, a slightly bigger interval, a slightly smaller. Yes, slightly smaller. The bigger the confidence interval, that means we are sort of do not care much about the confidence, then of course our interval becomes smaller. Okay, so alpha divided by 2 is 0.05. So then we adjust the quantiles for our bootstrap sample, and then we run this procedure, which is already there, right? So there's nothing much to change, except that alpha becomes 0.1 instead of 0.05. And then we will compute this bootstrap confidence interval for this value. And that would be this one, okay. And then as you could see, it's very, very close, okay. They're very close. This is the kind of, you know, like 1.15 and here 1.17. And this here it's also, it's very, they're really close to each other. That one of these rare cases when things are really nice. Usually, if you have very real data and a very big data, things are not as perfect as here. Certainly not. All right. Okay. What could you do? You could. In this particular case, what we did, we just this is our model. This is our data, and then we also plot the estimate, and it fits like almost perfectly. It's sort of very nice. It looks very nice. But it could be that in some case you just do this and then you have your data and you fit your plot, and it just, even if you look by an eye, you see, oh, that's just not good. It's really not good. So there might be reasons for that. The reasons might be that your maybe a model is okay. Okay, there could be that the model is okay, but the minimum is not found. Theta is just wrong. Okay, that could be. Just theta hat is just not the one which should be there. It's not a global minimum. It could be a local minimum, or maybe it's even a local maximum. Who knows? So you just really need to make sure it's a minimum, because you might find something else. So then of course, if you substitute instead of if you would have substituted the right theta hat, things would have been fine. But you've substituted something else, which is not a good estimator of the true theta, then of course you should not expect that things are going to be fine. Absolutely not. So that would be one thing. So it could be that procedures just fails to find a minimum, just find something, could just fail, you know. That's also, you see, because this theorem, of course, the one which guarantees that it's asymptotically normal, it is based on, you remember I said that, under some assumptions. Of course, those assumptions should be satisfied. So in principle, but you can actually never check that, because you never know the truth thing, okay, in principle. Of course, if you suggest the function f, then you know at least what are the properties of this function, should be differentiable and all that. That's all fine, but you never know the distribution of your errors for sure. Okay, that's the problem, and that could spoil the whole thing. So if distribution of the errors is okay, if it's for instance normal, then things are okay. Then there's a theorem which guarantees asymptotic normality. Otherwise, it's just not guaranteed. Okay, you can try different starting value. That's an art, especially okay, for one dimensional, it's not a problem, right? If theta is one dimensional, it's not a problem. You just simply try all of them. Okay, but if it's like already three dimensional, it becomes, I mean, what should you take? Because if you run through all three of them, well, it becomes a lot of values to try. Still might be doable, but in most cases not. I mean, in most cases, if theta is multivariate, and also have like, if you cannot throw away, if you cannot restrict the set of possible thetas, then it's just too much to. So you really need to come up with some ad hoc arguments where you could, which would help you, which would guide you towards the good choice of starting values. That's exactly the case in this last exercise of the assignment. So I'm really being curious whether people could find other starting values than mine, for instance. Okay, I would be glad to see that the other starting values will work as well, and deliver the same. Okay, so that would be sort of interesting to see, because this is really a real data set. There is no background truth. We don't know the background truth. It's not it's not available simply. And then, of course, the very last thing, the very last reason, and maybe the most important one, is that just your regression function is just the wrong choice. That's it. It's just a way to, of course, you can choose any function you want, but of course, remember that this difference y minus f could be something which is which doesn't satisfy any conditions you want needed for theorem to hold, and then so it just be very bad choice of the regression function in the first place. That's it, and then you really need to rethink and to try another function. Okay, I think we are good time to stop, to have a break. Let's have a break. Let's see what is the time now. Okay, we will start at 14:31. Okay, so let's have a break for 15 minutes, and please go ahead and put your questions if you have any in the chat. Okay, so now we have a break for 15 minutes. Okay, let us continue. Let me go through a couple of questions here. Is this delta method? Yes, it is delta method essentially. For those who know this method, for instance, if you're taking this course, asymptotic statistics, then this is one of the subjects in this course. It is about if say theta hat is asymptotically normal, then what can you say about f of theta hat, some function f of theta hat? And then of course it's also asymptotically normal, and then it becomes a different normal distribution. Well, this is delta method indeed. I was trying to avoid this, but and actually this is delta method and the property of normal distribution, the one which I was mentioning. Maybe I will tell a little bit more about this. This is kind of nice thing to know, actually. Let me say something about it on the other. Let me do here, share a whiteboard. So I'm going to this is a kind of a nice fact to know. For instance, if you have x, which is a vector which is normally distributed with mu and sigma, okay. So this is a multivariate normal distribution. This is the very nice property of multivariate normal distribution. And then you take any matrix B, okay, such that you can multiply. You make a new vector, a new thing, which is y is equal to bx, okay, and B is some matrix which have the right dimensions, so that you can multiply this matrix with x. So y is another vector, possibly with which has another dimension. And it is also normal with parameters b mu, and then bx, b sigma times b transposed. Okay, so this is it. So this is the very nice property of multivariate normal. This is for any matrix B. Okay, doesn't matter, as long as you can multiply. Of course, you have to say x is what is it, n by 1, for instance. Okay, it's just a vector dimension n, and then this is n by 1. Okay, and B say m by n. Okay, matrix. Then your resulting vector y is going to be m by 1. Okay, so your resulting vector I is now m dimensional. And it's another normal distribution, of course. This is the m-dimensional distribution. And for instance, a very interesting consequence is this. For instance, if you have x, right? So x is just like x1 and so on, xn, right? And it has normal distribution with some mu, okay, mu1 and so on, mu n, right? This is the vector. And then a sigma is actually like this: sigma 1, 1, sigma 1, 2, sigma, what is it, n, 1, n, and so on, okay, and so on. And then you have sigma n, n here. Okay, this is the matrix. Okay, so this is the parameters. So this is the, and then actually what you want to know, for instance, what is the distribution of x, say, xi, okay, the coordinate here, the one coordinate here. What can you do? You can actually take a vector a, okay, which is equal to, what is it, 0 and everywhere 0, okay, and only 1 at place e, okay, so here's eth place, okay, if you have this place. Then you can take A transpose times x, right? What will you get? Well, you will get xi. Okay, xi is equal to this. right? It's just this vector times, and this has to have distribution according to this formula, just A transpose mu, right? A transpose sigma A, right? This is what it has to be. And we compute, if you compute, so A is just a vector which has everywhere zeros and 1 at each place, then you can compute that this is equal to n, and then this A times mu is actually just mu A, mu I. And this, if you compute this, here everything, you just take this vector, which is just 0, 1, 0 times this, and then 0, 1, 0. If you compute this, you will see that you will get exactly sigma I, just the one element of this matrix sigma, which is on the diagonal place I. So you will get here sigma I. So therefore, we can conclude that the coordinate xi has a normal distribution with parameters mu I, sigma I. Well, we knew that, but now we can get it formally by using this property. Okay, so this is a very nice property, which, and actually you can also derive that any linear combination of normal vector is normally distributed. Any subvector of normally distributed vector is normally distributed, and you can compute its properties like this. Okay, so this is the very nice property of multivariate normal distribution. Okay, let me go on with the the lecture. So, there were some more questions. Let me look at those. I don't see them now for some reason. Okay, chat. Is there delta? Okay, in the assignment we do not. Do we need to prove asymptotic normality? No, you don't need to prove asymptotic normality. Absolutely not, because that's a very hard thing. It's actually part of this course, asymptotic statistics. So you just when you ask to compute the certain quantity using asymptotic normality, you just apply this formula which follow from asymptotic normality. You don't need to prove asymptotic normality. Actually, the question is as follows: is using asymptotic normality, compute blah 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 blah, whatever. Okay, and then it's not asked to show asymptotic normality. Okay, you just use asymptotic normality, and when you use asymptotic normality, then you know that these properties hold, and therefore you can apply them. Okay, is there any way to discuss the grading of the assignments with the TA? Yes, it is. You just approach them, and I would advise to show up in the practical session and ask questions about, and you can ask for feedback. Well, if there is already feedback there, but you can, if you want, you can discuss this feedback. That could be done during practical sessions, but also by email, I think. And if you really need it, you can also ask for an appointment with the TA. But I presume that should be enough that you during practical session. Actually, we got a third TA. You will start per assignment 3. So the assignment 2 will be still handled by 2 TAs, but starting with assignment 3, there will be new TAs, so there will be more people for you to help. But second assignment is going to be still handled by 2, Lena and Tessa. Okay, let me see where is my oh, so I stopped sharing now, but just because I didn't find where to. Okay, so we are here. So we treated this example, right? We plotted the fitted model. We discussed some problems, possible problems. Okay, here it is. Well, of course, remember that we could actually test for theta J is equal, that was at the very beginning. Let me just remind this. Here it is. So all these tests are present in the output of R when you create the model, right? Non-linear model, you create that, and then you say summary of that. What you will get, of course, all theta hats, right? The estimates of the coordinate of vector theta, but you also get estimates of the standard deviation, and you also get the values of these test statistics, and you also get the p-values when you test when r is equal to 0. So by default it's 0, and then you get whether theta 1, for instance, is equal to 0 or not. You will get this p-value, right? So you see that on the very last column of your output. We'll see. I will run today, hopefully. And then you would wonder, maybe I should, if H0 is not rejected, that means it's not too bad to assume that theta I is 0. So maybe I should remove it. So this is, let's see, this is here. So relatively large p-values means that maybe it would be a good idea to remove that parameter at all. So maybe it's just obsolete. It's not a good. This model is way too complicated. And also you could look at the correlation matrix, and maybe you will see that certain thetas are correlated with each other. Okay, so this is the correlation matrix of theta hat. This means it gives you. Well, it gives you actually, you will get covariance matrix, but you can compute correlation matrix. It's not a problem. It's actually better because correlation matrix is normalized. It's always between -1 and 1, all the coefficients, and then you can actually give meanings to the elements which are outside of the diagonal. So that would be correlation between corresponding coordinates of your vector theta. And then if this is close to +1 or -1, then of course that means they're linearly correlated. That means that basically they express the same thing. So they're more or less the same. So maybe it makes sense to throw away one of them. That would be another indication, is that your model is too complicated, too over-parameterized, basically. So you may want to remove 1 or 2 parameters from your model. You would like to test that. Can I remove 1 or 2 parameters, or maybe half of the parameters? Okay, whatever you think would be appropriate. And then you would like to test that. Okay, this is a very important thing. We are going to do this, but first let's discuss model assumptions. Of course, we have certain assumptions, right? Again, I remind that we can, of course, compute residuals. They can be computed. If once you feed the model, you can say residuals of the model, and then you will get those things, which are supposed to be estimates of your true errors. And we assume that our errors are independent, and they also have the same sigma. This is very important, that sigma is the same, it is not changing. And also that they have expectation 0. So that you could check, okay? You could have a look at the plot of fitted values against residuals. That's exactly the same thing what we had in linear regression. You do the same here. The only thing is that, of course, you can also test for normality, but normality is not required here. You just test for that and see, oh, and then you can say, oh, it's actually, maybe they're also normal, okay? They look normal, but it's not really required. What is really important is to look whether there is this particular pattern and this fitted against residuals, and also whether residuals are, well, especially the fact that variance is the same, okay? So that it doesn't change. That would be a thing to look at. Also, whether it's symmetric or not, but it's again not really required, actually. Yes, because if it's normal, then of course it should be symmetric, of course. But in principle here, it doesn't have to be symmetric, but what it has to kind of look like its expectation is 0. So they have to be around 0, that's for sure. They do not have to, if you see that all of them are concentrated in, say, positive half, then that would be also a bad indication that your model is not really good. So at least some things you could tell by looking at this at these checks. Well, and then there is advice that maybe you want to do some transformations. Well, as I told you, transformation of the covariates is not a problem. You can always do that. You just lose interpretability. So your original x was something, and then you take a log of that. So then it loses its original meaning. But it's not a problem at all, absolutely not. It doesn't change the model. In principle, it just changed the names and it changed the the meaning of the covariates. But if you apply transformation to the response variables, then you're really changing the model drastically. Okay, so that is something which is done. Okay, so one has to be kind of a bit cautious about this. Applying transformation to response variables changes completely the model. So it's not your model like y is equal to f plus noise. It is now f of y is equal to some function plus noise. So you see, these are completely different things. Okay, but again, you can always look at the whether your errors are normal or not by looking at the quantile plot of residuals, and also can look at also at the histogram of the residuals. That's also possible to look at. All right, this is what we do here. We just have a look at the fitted against residuals in our example, and we see that there is a problem here. Okay, so if you see something like that, you need to sort of report that. You really need to say, oh, actually, I did all this analysis, okay, but as I could see that the residuals, the variance is not constant. So you see the variance, okay, it's from minus something to plus something, but I would say it sort of has more values here on the positive side than on the negative half. And also we see that the spread is changing, okay, it's just bigger spread here. So that's not good. That you would conclude here that the regression function fc of theta may not be appropriate for this data. Okay, although we had very nice confidence intervals, remember they were very, very small. And now if we look at the normal, okay, so we already sort of know it's not a good model, but just okay, is it normal, or are the residuals normal or not? Well, certainly not. You see there's something here. And also histogram of the residuals is also doesn't look symmetric thing. Okay, that's it. That would, you just produce this and shortly report on this or what you see. Okay, here's one important piece. It's a bit mathematical, but this is important, and I can tell you that there will be certainly something about this in the exam. Okay, so I will include this part in the exam for sure. Okay, so comparing nested models. So what is it? It's actually exactly what we started just in this second half. Well, remember we have these thetas, and some of them, the hypothesis that some of them are zeros was not rejected. So maybe we should remove them. Okay. So if we remove them, we get another model, right? So what is removing? Well, removing in this particular case means that we put them to zeros. So there is a vector theta, okay? And then test says like first and second coordinates are actually 0. Okay, what can I do? I can put them to zeros. I just set them to 0. And then of course I get another function. That function is going to be dependent only on the other parameters. So the two parameters will be gone. So my theta is going to be of a less dimension. So what I'm doing, I'm actually looking at the submodel, okay, reduced model. And I want want to know whether this reduced model is as good as the one before, as the big one I started with. I want to test that, and I'm going to do that exactly as I did this in linear regression. The idea is exactly the same. So this everything becomes approximate. That's the only difference. In linear regression, everything was exact. There was f test. There was chi-squared divided by chi-squared. Remember, fit of the bad model minus fit of the reduced model minus fit of the big model divided by the fit of the big model. That was F distribution. That idea I'm going to apply here as well. Exactly. Everything is the same. That's why these linear regression things are very useful now. But everything becomes just approximate instead of exactly as it was in linear regression. It was exact. Everything was exact. The distribution of test statistics was exact, but here it becomes approximate. But other than that, it's all the same. Okay, let us formalize this. We have a theta p, okay, and there is a theta q, okay, and this theta q is theta q is a bigger dimension, so that's a bigger model, a bigger parameter, and theta p is a subvector of theta q. Actually, again, I forget to, I made a pre-recording and I made this remark there, but I still didn't correct this. This has to be RQ, okay? So because this is vector theta q, which is a q dimensional, so it has to be q here. I will correct this today. And this vector theta q consists of two things: the subvector theta p, which is the one which describes a submodel, reduced model, and the rest. Okay, there is something which is free for theta q. But then, so there is this theta q, which is big, and there is theta p, which is small, which is inside theta q. And this corresponds to a big model and a reduced model. When do we get reduced model? We will get reduced model from the big model if we just put part of that part, which is free in theta q, equal to some values. So think of some vector A, which is from the space q minus p. We fix them. Some of the coordinates of theta are fixed now. We put them to some values. So this means that our variability, our flexibility becomes smaller, becomes less, right? So we only have theta p which varies, okay? So this one is the vector theta q, where we leave theta p free, but this vector, subvector, we put fixed to some value, okay? So that boils down to the two models. One is just where everything is free, and here part of the vector theta is fixed. So therefore, this becomes a smaller model, a reduced model. And we want to see whether this model is as good as that model. So here we have theta p, which has p dimensions, and here q dimensions, and p is always less than q, okay? Of course, there is a connection between these two. So this function here is actually this function, exactly that function, when we put constants instead of this part which is which was free in theta q and which is not absent in theta p, which is just not there. So, okay, I hope this is clear. This is just formalization of the thing that if you just have theta, which has q coordinates, q coordinates, and you say, okay, I leave p coordinates free, but the others I fix. I say they're equal to some constant. Then, of course, the dimensionality reduces, so I will get another function, okay, in principle. So that function becomes this. And I want to know whether this new model, where I put certain values on my theta to certain values, I fix them, whether this is as good as this one. Okay, I want to know that. Okay, how do I do that? Well, I do that exactly how I did this in the linear regression. I compute the fit of the big model. Okay, this is my fit. That's the best I can do when I fit the big model. And then I fit my small model, submodel, reduced model. The submodel of this omega small is the submodel of omega big. I compute fit of that model. So I have two fits. Of course, I know for sure this is going to be smaller than that one, smaller or equal. Why? Because I have less freedom here. So my minimum here is going to be bigger, of course, because I have less things to vary. So because it's a submodel. So here I have more parameters to minimize, over which I can minimize. Of course, this fit is going to be always better. So I know for sure that this is going to happen. I only want to know whether this difference is big or not. Okay, if this difference is big, that means, well, my big model is really doing well compared to a small model. My small model is not really good because I lose a lot of fit when I go to a smaller model. I should not lose that much fit. I'm allowed to lose a little bit of fit. Then I would say, okay, then my small model doing as good as the big model. So this is exactly this idea. If this difference is large, then omega is not adequate. That means it's not doing well, reproducing the big model. Okay, of course, so I take this difference, divide by sigma, and this should be approximately chi-squared. That's exactly the same idea as in linear regression. But again, sigma, I would base my test on this quantity if I knew sigma, but I don't know sigma. So I substitute instead of sigma, its estimate. Okay, and then what I will get one chi-squared divided by another chi-squared, and they're approximately, okay, they're approximately independent, and they're approximately chi-squared distributed, like in linear regression. So basically, I apply the same reasoning as linear regression, but everywhere I have to say approximately. So it's going to be chi-squared, normalized chi-squared divided by normalized chi-squared, approximately independent, and it has to be F distributed approximate to that thing. This is how I do my test. Okay, so I simply compute this quantity, which I can do, and compare to the F quantile. Alternatively, I can compute just the p-value. What should I do? I should take some random variable f, which has this distribution, f distribution with q minus p degrees of freedom and minus q degrees of freedom, and then I compute the probability that this random variable is bigger than the value of that statistics. Okay, and then if this p-value is very small, this means this value is very big. This means I have very big difference, and this means my omega small is not good, it's not adequate. So it's not doing well. So therefore I will, in that case, if p-value is small, smaller than some significance level, which I should predetermine beforehand, then I reject H0, which says that omega is adequate. No. Omega is good. Yes, that would be H0, and that I would reject. Right? Yes. Yes, that would be saying that omega is not adequate. Okay. That's it. This is how you do this testing. That's a very general idea. So it's all about what is your choice of omega big and omega reduced. So in each concrete situation, you need to look into this and see, okay, the question, how can I frame this question in this setting? So you need to understand what is here a global model omega, what is here a reduced model, and what do I need to do? Once you specify these two, that's the most important step. You just specify what is global model here. Okay, this is this one. with theta is equal to this, how many coordinates it has. And then what is the reduced model? Okay, reduced model boils down that actually just theta 3 is gone, for instance. Theta 3 is equal to 0. Okay, then you understand what is the relation between the global model and the reduced model. And once you know that, then of course you can do the testing. Okay, let's see. Okay, this is there are other things. How can people compare the nested models? The Sakaike information criterion, Bayesian information criterion, Mal's CP criterion, cross-validation, and there are others. There are a combination of these two. So this is just one way to look at these things. So these things, AIC and BIC and Mallows, these are also classical things. This is how you choose the model. What we are doing here, we are choosing the model. You can do this. You can compare the big model, the small model. Okay, this is only looking when one model is a submodel of the other. Okay, then you can do this. But imagine you have two models which are not such that none of this model is a submodel of the other. So they're not nested. Then you cannot apply this machinery. Okay, so that what you can apply this machinery. Okay, I for instance also do research in this. So this is one of the most important questions in statistics and data analysis. What model should I take? It's called selection model. This is a very global, a very important problem in statistics. You have a whole bunch of models. Which model should I take? Which model is the best? So there are many approaches. There are a lot of things. Here we just looked at the situation when one is inside the other. Okay, but they don't have to be. Let's have a look at the example. So let us just probably all these notions will become clear now. So our big model, remember, this was our function f, where we had theta 1, theta 2, theta 3. Now let theta 2 equal to 0. Just put it to 0. So your f becomes this. It's something else. So, and there is no theta 2. There is only theta 1 and theta 3. So we have now a submodel. This is the reduced model of our original model. And we want to know whether this model is as good as the original one. Maybe theta 2 is absolutely irrelevant. Maybe we should throw that away. And it seems like theta 2, well, I don't know exactly remember whether it was, whether the test said that theta 2 should be 0 or not. I don't exactly remember that. But suppose it was like that. Then we are thinking, oh, maybe we should throw that away. Maybe it's 0. And then put that to 0, we get a reduced model. And now we want to know whether this reduced model is as good as the previous, the big model. Okay, so we compute the sum of squares for this reduced model. Okay, I write here theta 2. What this 2 means is that we have now 2 parameters, not 3, 2. It's theta 1 and theta 3. So it's a vector. This one is a vector which consists of 2 parameters, theta 1 and theta 3. Theta 2 is not there anymore. It's gone. It's 0. And in the full model, it was theta 1, theta 2, theta 3. And then, of course, they were different. So here we'll have 2 different estimates of theta 1 and theta 3. They are going to be different than those which were obtained previously, where we also had theta 2. So this is sum of squares for the model. For the reduced model, this is sum of squares for the full model, feet, remember feet. We see how big difference becomes. So this is really a big value. So that means feet is very bad. So by removing theta 2, we are actually making things very much worse. Okay, but let's make it very formal. Let's just take this one minus this one divided by Q minus P. What is Q? Q is 3. Okay, original big model was 3-dimensional. Minus reduced model. This is P. This is 2. 3 minus 2. And here is the sum of squares of the big model divided by n minus P. Remember, n is 176 minus P 3. Okay, so this is estimate of sigma squared. and we compute this huge value, okay? And we should compare that to just F quantile, which is much smaller. So this means we reject H0, and H0 was omega small is adequate, is relevant. It is not relevant, it is not adequate. We should not go to a smaller model. So throwing away, putting theta2 to 0 makes fit too much worse. Okay, so we reject the reduced model. Okay, I hope things are clear here. That's it. Let me have a look at the very quickly demonstrate some R simulations. Okay, so if there are questions, you could put them as well. But let me just go through the where is R? There is no R, by the way. I have to open it, otherwise it's not. So share RStudio. Okay. So this is well, this is this data set. Let me just go through this quickly. This is what we did. This is the covariance matrix, remember? So this is the theta1, theta2, theta3. This is our big model. This is the estimate here, okay, the coefficients, theta1 hat, theta2 hat, theta3 hat. Okay, this is our confidence intervals, okay, for all of them, based on asymptotic normality. We computed them, okay. So this is available at the on the canvas. Of course, you can download this file and have a look at this. And here it is, this bootstrap. Okay, let me just demonstrate. So it's 100 here. Okay, just very small. To make it quick. Otherwise, I think it's still quick. Let me put 1000. Let's see how it works with 1000. I think it shouldn't be a problem. Okay, just for this is just preparation, and let's run. Now I'm running the bootstrap procedure to fill in this array of estimates, theta star. It's fine, you see, it's fine. It sort of gives very quickly. Let's just put here 10, okay, very bad initial value, and I think it will fail then. So I try. You see, it fails because my choice of the initial value is very bad. I took theta3 equal to 10, where it was 1, and it sort of, so it is not able to compute it. See, so let's go to 1 back, and then it's gonna do well, I think. Yes, and then we compute just according to this procedure, upper bound and lower bound of upper bounds and lower bounds for our theta. Okay, so these are the bootstrap confidence intervals. Okay, and now we do this for this value f of 4. So what can we do? We can simply put the theta hat instead of theta. That would be our estimate. Okay, this is what we can do. This is the value. So this is the estimate of f of 4 of theta, and instead of theta we put theta hat. You see coefficients of the model. Let's compute gradient. Okay, I did this, but actually I think you could have packages which compute gradients of the functions. So I did this just by myself manually, and then I compute gradient vector at point 4. Let's see. I have to. Well, I get 3 numbers, of course, right? Just have a look. Yes, there are 3 numbers. This is exactly this vector, the estimate of the gradient vector at point 4, right? And I put theta hat there. Then I can compute all the things I need, and I put lower bound, upper bound, and then I will get the confidence interval based on the asymptotic normality. Okay, here it is. Okay, a bootstrap, do it yourself. Okay, so it's just actually basically repeating the procedure which is before. Let us have this thing. Let's run the, just create this a grid, okay, and actually I already have this. And then I will create many lower bounds and many upper bounds, okay, for each value of X, for each value of C. So, and then I can plot data first, and then I plot a fitted curve, okay, and then I will plot all the segments, all the confidence intervals for all X's, okay. So this is what I do. I can do that also in another style, in the polygon thing. You see, it's too good actually. And then a line, I can put the fitted line as well. Okay, and here is this checks for the model assumptions. Okay, so let's just have a plot. That's exactly the one, fitted against the residuals. It's very easy. You just put fitted of the model against residuals of the model. If you want, you could put some line just to see where the zero line to sort of the one which, well, your residual should be symmetric around that line approximately. Okay, and then QQ plot. Okay, so this is just and a histogram. Okay, so we've seen that. Okay, here's this comparing to the nested model. Let's just create a new model with theta1 and theta3, and theta2 is equal to 0. I put this just equal to 0. Then I create a new formula for that, and I create a new model, okay, the reduced one, okay? So now I have two models, our initial model and our reduced model, and I do another one inside the other. That's it. That's very easy in R, okay? So let's just do that. And you see what we get. We have sum of squares here. This is sum of squares of the small model. This is, by the way, I did this wrongly. I should have done this, but it doesn't matter. You should do like model one inside the other, then it will be in the right order. Okay, then you will get something like that. Well, actually, it's sort of okay here as well. Doesn't matter. You just switch the lines, but you will get the same p-value. So anyway, so this is the reduced model, and this is the big model. Okay. And then this is the value of statistics, and this is the p-value. Okay, so everything is here, and this divided by that, this is this value, and then this divided by that, this divided by what I don't exactly remember, but that's in the formula. What we can do this just by hand. Okay, just sum of squares for the big model. This is the for the big model, okay, sum of squares. This is the one. That's exactly the one which is here. See, so sum of squares for the big model is here, and then we can do the same for the reduced model. We simply sum all the residuals, squares of all the residuals. That's it. This is what we do. So this is the, and that's exactly this value which is here, okay, which simply reproduce the values of this table. Then we, when we compute the value of the statistics, okay, that's this number, okay, that's just one minus another divided by, okay, we have to make a difference, okay, of these two and divide by the SSQ, and that would be exactly this value, okay, this value of the statistics is here, and we reproduce it like this, and then p-value. Okay, p-value is just the right tail of what we compute here, and the probability that a random variable with this distribution, with f distribution, with q minus p degrees of freedom n minus q, that is bigger than this value f. Okay, that's exactly this value here. Well, it's 0 here, but it's 2 to the power. Okay, well, that's so what we compute here are sort of approximated it as 0, whereas here it's sort of very small numbers. It doesn't really matter. Okay, here is a criterion, which is also there. I could sort of use those. And the idea is that you take the one which is, let me not go into that, so because I didn't explain what the archaic information criterion was and also what the BIC was, Bayesian information criterion. So this is very important. This part is really important. So please try. I really urge you to make an effort and understand what this is. Just testing that a smaller model is appropriate within a bigger model and how it goes. Also, both theoretically and practically. Okay. Okay, that's all for today. So if you have questions, please go ahead and ask. So let me stop sharing here. This is it for today. And next time, please remember that next time is going to be a practical session. Okay, so we Tessa and Lena, they should set up 2 meetings. Last time it was a bit not equally divided into groups. Tessa got much more than the half. So now groups from 1 till 15 are going to be in one group, and from 16 till the end, and all the others, all the people without group, they're going to be in the second group. Okay, so because it was unevenly split the first time, so we'll split it more evenly this time. But they will have to set up this meeting, and you will see that appear on Canvas, and they probably also should to announce that. I will ask them to set up these 2 meetings for next time. So please go ahead and make assignment 2 and prepare your questions so that you know, well, you will have to be already busy, of course, because there will be not much days left after practical session. So it's a very short couple of days before the deadline, I think. And also concerning your questions with respect to the feedback for the first assignment, you can also direct to the questions and have some discussions with Lena and Tessa during practical sessions or by email. Okay, that's it for today. I'm ending this meeting. I'm waiting for a little while. If you have any urgent questions, please go ahead and ask. Otherwise, I'm ending the meeting. And have a nice day. Okay.